All right, everybody, we have a request to do a retrosynthetic analysis from fall 2019, and here it is. We have to make this target molecule right here. It's worth 30 points. It's a pretty big deal. What are we allowed to use? Saturated alcohols of 5 carbons or less, benzyl alcohol, and benzene. So benzene is what you're going to use for the electrophilic aromatic substitution. Speaking of which, we have to know about directing groups. For example, on our target, we have a directing group here that's a primary R group. Itself is an OP director, which is good news because I see a group that is actually para to it. Remember though, primary R retros backwards to R carbonyl phenyl, which is an acyl group, which is a meta director. So you can use the acyl group as a meta director before you reduce it to a primary alkyl group. This is also good news. I have a group that's meta to the primary R group. I have a strategy in mind now. I'm going to put the acyl group on benzene first. I'm going to do a sulfonation to put the meta sulfonic acid, which I can deprotonate at the end. And after I reduce this, it's now a orthopara director. I'm then going to put on somehow the oxygen group. We don't know how to put it on an oxygen group. The closest one we have is an hydroxyl group, which is an oxygen group, but we can't do that using electrophilic aromatic substitution. You have to first make a phenol from a diazonium species. That's the only way you know how to put an OH on benzene. And then we'll do our ether synthesis after we put the OH on benzene. So that being said, and as I've said many times in lecture, this is a retro where you can actually do the forward synthesis first, especially since I gave you the whole strategy verbally. Let's go with verbally becoming a written document. Here's benzene. Here's my synthesis starting over here. I want to put this acyl group on benzene. Right here. Oh, let's put it on there where it looks like it's in the picture so things don't get rotated in your brain. Oh boy, I can't. Well, it's close enough over here. Carbonyl. 5 carbons, 1, 2, 3, 4, 5, 6. Oh, 6. We'll have to deal with that later. 1, 2, 3, 4, 5, 6. And that's going to involve acylation, which means you need a chlorocarbonyl. 1, 2, 3, 4, 5, 6. I think we got 7 now. 1, 2, 3, 4, 5, 6, 7. Yeah. Sorry. Here we go. 1, 2, 3, 4, 5, and 6. And the catalyst for this reaction, the catalyst for putting on carbon groups on benzene is always AlCl3. AlCl3. You're also going to have to design a synthesis for that acyl group. This acyl group right here. So we can do that maybe a little lower. The 6 carbon acyl group, but we're not allowed to start with 6 carbons. So let's talk about a 5 carbon alkyl group. right there. We've lengthened alkyl groups many times. We can lengthen them by 1 or 2 rather quickly by first making them into Grignards and attacking either an aldehyde or a ketone, or attacking an epoxide. So we need to make it first into an alkyl bromide. Then an organolithium. And that's done with lithium and hexane. And then we got to extend it by 1 carbon. We did learn a reaction that just recently where you can get a new carbon directly to a carboxylic acid. And it's not on the list, but it's not organic either. It was using carbon dioxide with an organolithium. This will save you a couple steps if you can remember that. Step 1, CO2. Step 2, HCl. And you have your 7 carbon or your 6 carbon carboxylic acid. Here's your new carbon. 1, 2, I think I have 7 again. I keep doing that, don't I? 1, 2, 3, 4, 5, 6, 7. Oh, it's too big. There's the new carbon right there. And of course, we are experts at making those into, all right then. We are experts into making those into acid halide. We've been doing that for a little while now. And that one is just SOCl2 pyridine, acid halide. So that piece we need to put on benzene, which we already showed how. And that's up here. And we're off to the races here. Let's see, what's this? 1, 2, 3, 4, 5, 6. Oh, goodness gracious. I'm thinking ahead here, and I'm just thinking ahead. Next group, I'm going to use the meta-directing abilities of this ketone to put the sulfonic acid on. This is time for this before I reduce this to a primary R group. So I'm going to put the sulfonic acid on there, and I'm tired of drawing this group, so I won't draw it anymore. R. Benzene. Meta-directing, we'll put a sulfonic acid right here. If we use the right conditions, which are H2SO4 and heat. And you've got your meta-sulfonic acid as promised. And it's time to change that R group into a primary R group so that we can take advantage of its para-directing ability. So now we need to draw it out like this. And of course, I didn't leave enough room. Here it is. And primary R group. There you go. So we're taking a ketone right here, and reducing it all the way to this. Any suggestions? There's 2 suggestions. One is to use the Clemmensen reaction, which is probably advisable here. because this is an acid, and the Wolff-Kishner reaction involves using a base, which will first react with your acid. And you want to avoid that. So Clemenson's probably a better choice right now. And we'll use that in, I don't know, purple. Zinc, amalgam, and HCl. If you're curious, there's your two H's from HCl. And it's now a primary R group, and we'll label it as such so we don't have to draw it again. R prime. And the job is now to get in this position. I know we lost sight of our target, but the last group has to go here, ortho to the SO3H, para to the primary R group, ortho to the SO3, para to the R group. And the protocol is the diazotization protocol. Our last review day notes has the protocol in it. Sorry, I just posted them this morning. I usually do it right after class, but I guess stuff's going on and I didn't get to it on Monday. Here we go. Diazotization protocol involves first nitration. You can't skip steps in this protocol. You can't invent your own protocol. You've got to put a nitro group on first. And that involves using nitric acid, sulfuric acid, and heat. And now it's time to reduce that nitro to an aniline. That is to say, an NH2. So I'm just going to put a box around things here. Keep this away from the other section here. I'm going to loop around that yellow box. We need to make R prime, phenyl, SO3H meta, NH2. How do we do that? Well, we got lots of ways. Your R prime, you don't have to worry about it being reduced. It's already produced. So you can use your old friend lithium aluminum hydride and HCl if you want. Or I typically suggest that you always try to use this one, H2 and nickel. I'd only avoid using that if there were alkenes around, because I don't want alkenes being reduced. There's no alkenes. Don't talk to me about benzene alkenes. Those aren't alkenes. That's an aromatic ring. Okay. And I'm just breaking this down to steps here. Diazotization protocol needs to make that into a diazonium ion. Right down here. How tall is this page? It's pretty tall. Let's try not to make it taller after this. SO3H here. Diazonium ion here. And R prime. You need sodium nitrite. NaNO2. NaNO2. You need HCl. Excess, you need a lot of water. AQ, you need not a lot of heat. This is one where I need to see the heat. I'd be okay if you forgot this heat over here. I'll forgive you. I will not forgive you here if you don't tell me it has to stay at 0 degrees Celsius. Because if you don't, then you just successfully made a phenol. The use of the word success was inappropriate there. You do not want a phenol here. Oh, you do? Oh, wait, you do want a phenol here. But I want to make this consistent. You always need 0 degrees here. How do you make it into a phenol, which is one of the 7 options from this point, and it is the option I want, then you say water and room temperature. Now, if you did see that you already had water in the reaction previous, you could have covered this by doing this. Be very careful, though. Instead of doing it that way, you could have done it this way. Cross that off and say 0 degrees Celsius to make the diazonium ion. You have to do that first. Then you let it warm up to room temperature. And you've accomplished what I had with that second reaction in this reaction. There's water present. You warmed it up to room temperature. You're going to get your phenol. We're well on our way. R prime. Well on our way. We now have OH there, purple. We have SO3Na. We don't have SO3Na. We have SO3H. Eventually we'll have SO3Na. So we got that going on. Trying to make it a little tighter here. The OH group needs to be made into what? Here it is. The OH needs to become an ether. We've been making ethers for a better part of a year now. Take the H off the alcohol. Do an SN2 on a 6-carbon group with a leaving group, which we don't have. What we can do here is right here in a different color. One, CH2O, 2, HCl, and you've made this 6 carbons now with an OH that needs to become a Br. And we'll just extend our yellow box a little bit. Not too much. Needs to become a Br. That's PBr3. We haven't had a retro yet where we haven't used a reaction like that, right? Or we already had one already. Look right here. So that piece is needed to make our ether. 1, 2, 3, 4, 5, 6 carbon group. 1, 2, 3, 4, 5, 6 carbon group. So we need to do our ether and be done with it. This is going to take us to our target. And big screen, big screen. Still don't see the target. Wow, big barely. All right, here we go. I can get there. I have to use base to take the H off. KOH takes the H off. Step 1. Step 2. 6 carbon group with a Br, which you made right here. 1, 2, 3, 4, 5, 6, yeah. And that takes you to your target. Make sure you use excess KOH. 2 reasons. Oh, it should be NaOH. But you know what I'm saying? No, I don't think you do. Not very clear on that one. Up here, it says SO3Na. Do we really even care ever? As long as I get to SO3 minus, I'm happy. So I don't care what the spectator is really. And I think we have everything needed, except we have to pretend it was a retro now, or else we're throwing away half our points. We don't throw away half the points. We did all the hard work here. And you just say stuff like, well, I guess I needed it still big. This came from this. So hot pink. This molecule came from its precursor here. And this species here, this and this gave that. And this thing came from this thing. Which came from this thing. Came from this thing. And that came, kind of therapeutic here. And that came from there. Oh, my retro arrow is getting a little un-arrow-like. And that came from here. Which came from benzene. And what about these guys? This came from this thing. Which came from this thing. And that came from this thing. Which came from, this thing. Crossing retros. We also had a side retro that, this thing came from this thing, which came from, that and that. And sadly, we have to show formaldehyde coming from H3COH gives H2C OO using PCC. And I don't even know how to show that because it's going to be a big mess. Well, there's the formaldehyde. I just need a retro arrow here saying that came from that. And I think I've accounted for all my carbons in a retro fashion. This one here was taken care of here instead of here. And that's the retro, and I think that's a pretty good segment. Big picture, fits on a screen, and save. And we'll see you for the next one.